Okay, so now that we've learned a whole bunch of things that we can do with alkynes, triple bonds, we're going to learn one of the most important things that we can do, and that's to make new carbon-carbon bonds by alkylation of alkynes. And this leads to a bunch of synthetic strategies where we can use it to synthesize new compounds. So triple bonds, alkynes, can do an SN2 alkylation because we've seen earlier that we can deprotonate if we have a terminal alkyne or on the end, it has a hydrogen. You can add strong base. The bases that you would want to use in general are going to be sodium amide or butyllithium, and that's going to make the anion here. And this anion, it turns out, makes a really good nucleophile to do an SN2 reaction. So we can take it and then add a good electrophile like methyl iodide, which is really good for SN2 reactions. The carbon is going to be the nucleophile. It's going to attack the methyl iodide carbon and make a new bond and kick out the iodide. And so now we have made a new bond between the triple bond and the methyl from methyl iodide. So this is a new bond here. It's good for synthesis because it makes new carbon-carbon bonds, which are one of the hardest things to do in synthesis. Okay, just to recap, if you have the anion, the terminal anion, you can also add a more complicated electrophile, like I think this is propyl bromide, and it will also do an SN2 reaction and it'll make a new carbon-carbon bond. It gives you bromide as a byproduct, which is not, you don't always draw, but it's there. Works best with a primary alkyl halide, possibly secondary, definitely not tertiary, but primary is definitely the best one, and secondary in a lot of cases. You can do a double alkylation if you have acetylene to start with. So acetylene has two hydrogens on each end, and if you add excess base, butyllithium, it's going to deprotonate both of these carbons. And then when you add at least two equivalents of methyl iodide, it's going to put methyls on both ends here. So that would be a dialkylation reaction. And you could do that if you want it symmetrical. It's also possible to do it stepwise, one step at a time if we want to add different groups on either end. This is definitely more complicated, a little tougher to do in practice. But starting with acetylene, add specifically one equivalent of base and it will just deprotonate one side, and then one equivalent of the, in this case, ethyl bromide. It'll deprotonate one hydrogen and then it will add just on one side. And then once you have the middle compound, you can do it again, add another one equivalent of base, butyllithium, and add another halide, in this case butyl bromide, and it will add on the other side. It'll add over here. So we'll get the ethyl group on one side and the butyl group on the other side. You have to do it in two steps. You cannot combine it or you'll get a big mixture. So you have to specify that it would be one step at a time. So now we have a way to interconvert single, double, and triple bonds. The only thing that we haven't learned yet is this reaction here, how to start with alkanes and then turn them into double bonds. We'll see later that we can do that using radical reactions, but we've learned how to go back and forth between double and triple bonds and how to go from a double bond back to a single bond. Okay, so now the synthesis that we are going to be able to do is gonna really ramp up and get a lot more interesting, definitely more complicated. I'm going to do this problem in pretty great detail, and then I'm going to give you a bunch of problems to do. And I'm just going to print out the key rather than make it in the video because I think it'll be more useful that way. But we're going to spend quite a bit of time at this point from here on doing synthesis. We've learned a lot of reactions now, so we're going to be able to combine substitution reactions, elimination reactions, triple bond reactions, and now this alkylation, and make pretty complicated products. So this one here, we're going to start with our starting reagent is a cyclohexane with a 2-carbon chain that's a double bond. And our product that we want to make is, again, cyclohexane. Nothing's going to happen to the ring here, but it has 3 carbons and it still has a double bond. We're going to have to take this double bond, turn it into a triple bond, which we know how to do, then do the alkylation to add a 1-carbon group, and then take our triple bond that we have then and turn it back into a double bond. So I'm going to do this. This is like 5 or 6 steps, and then you're going to get a lot of practice. So follow along and just think stepwise, and then you'll have a chance to practice things like this. They will they'll be at this point now. We've learned enough that we can do pretty interesting synthesis. So the first step that we do is take our double bond, do a dialkylation using bromine. You could also use chlorine here. The solvent would be something that doesn't have any protons on it, like carbon tetrachloride, and it will add bromine across the double bond. The next step would be to do a double elimination. So adding excess of the strong base, it will eliminate twice to make a double bond and then a triple bond here, and then doing a water workup to reprotonate the triple bond, the terminal alkyne. So now we have a triple bond and we are able to do an alkylation. I'm showing both steps here. So the first thing we would do is add the strong base like butyllithium, and it's going to deprotonate here. This we would not put in a bottle. I just wanted to spell everything out clearly. So now we have our good nucleophile, and to that we can add methyl iodide. So the carbon nucleophile is going to come in, kick out iodine, and it's going to methylate here. Now we have the triple bond, and we have one more step to turn it into. We need to turn it into a double bond, but we need it to be a trans double bond. So the reduction that we would do would be the liquid, the sodium and ammonia, the liquid metal reduction, and that would give us the trans alkene at the end.